The sun, our life-giving star, is a force of both creation and destruction. Its warmth sustains every living thing on Earth, but beneath its glowing surface, unimaginable power is unleashed every second. It is also a cauldron of violence, a place where titanic forces collide and erupt in spectacular displays of energy. The sun hurls out solar energetic electrons, SEEs, at nearly the speed of light, sending them racing across the solar system in a cosmic storm. For years, we detected these electrons at Earth, registering their arrival with our instruments, but their exact origin on the sun was a mystery that eluded us. Imagine trying to trace a single raindrop back to its birthplace in a raging storm. That was the challenge scientists faced, a puzzle as complex as it was fascinating. The sun's surface is a chaos of explosions, with eruptions and flares happening constantly, making it nearly impossible to link a specific event to the electrons we detect millions of miles away. We saw eruptions then, sometimes much later. These electrons would hit our instruments, but the timing and connection were always uncertain. The connection was there, but the details were lost in the noise, buried beneath layers of data and cosmic interference. These electrons matter. They're a key part of space weather, capable of disrupting satellites, communications, and even threatening astronauts who venture beyond Earth's protective shield. To protect our technology and our explorers, we needed to know where these electrons came from before they started their journey toward us. The answer required a new approach, sending a probe closer to the sun than any spacecraft had ever dared, braving the intense heat and radiation. Only by getting up close, flying through the sun's outer atmosphere, could we finally connect the dots between solar explosions and the electrons that reach us here on Earth. This quest was about more than curiosity. It was about safeguarding our future, protecting our technology, and ensuring the safety of those who explore space. We had to leave Earth's vantage point and meet the sun on its own terms, venturing into a realm where no human or machine had gone before. The time had come to unravel the explosive origins of these superspeed electrons, to witness firsthand the forces that shape our solar system. The story of how we solved this cosmic puzzle is a testament to human ingenuity, determination, and our relentless drive to understand the universe. It's a journey from mystery to discovery, from danger to understanding, a transformation that changed our relationship with the sun forever. And it all began with a daring mission into the sun's domain, a bold step that opened a new chapter in our quest to unlock the secrets of the cosmos. Enter the Solar Orbiter, a joint ESA and NASA mission, our scout in the inner solar system. Unlike previous spacecraft, it flies close to the sun, enduring searing heat to capture both images and particles. Its unique power, linking a solar eruption it sees with the electrons it measures moments later. For the first time, scientists could match a burst of electrons to a specific explosion on the sun. This dual perspective finally separated the two main sources of these furious messengers. The Solar Orbiter changed everything we knew about the sun's most energetic particles. The Solar Orbiter has given us a new window into the sun's most powerful and mysterious outbursts. It revealed that there are actually two distinct birthplaces for superspeed electrons that race through space. First, solar flares. These are brief, intense flashes of energy that fire electrons in narrow, focused beams, like sprinters bursting from the starting line, traveling at incredible speeds. Second, coronal mass ejections, or CMEs. These are massive eruptions that launch huge waves of electrons and plasma, spreading out over hours and covering vast distances. In the past, we couldn't tell which electrons came from which event, making it hard to predict their impact on space weather. Now, with new data, we can finally distinguish the quick, sharp burst of electrons from a flare and the long-lasting, sustained surge that comes from a CME, which can last for hours and even days. This distinction is crucial for protecting astronauts and satellites. CME-driven electrons are far more energetic and dangerous, posing a greater threat to technology and human life in space. Thanks to the Solar Orbiter, we can finally read the sun's signals in real time and know what's coming our way, giving us a vital early warning system. It's like hearing both the crack of a bat and the roar of the crowd, two stories, one dramatic event, finally separated and understood. You'd think electrons traveling at incredible speeds would reach Earth in just a few minutes. But in reality, their journey across the vastness of space is anything but straightforward or simple. The The space between the sun and Earth is filled with a tangled web of solar wind, swirling plasma, and ever-shifting magnetic fields that create a chaotic environment. Electrons don't travel in straight lines. They spiral and twist along these invisible magnetic highways, zigzagging through turbulence like cosmic pinballs bouncing off obstacles. This cosmic obstacle course, full of twists and turns, slows them down dramatically, delaying their arrival at Earth by several hours. The solar orbiter, positioned close to the action near the sun, has given scientists an unprecedented opportunity to study this challenging journey in remarkable detail. They discovered that the complexity of the magnetic path, combined with the turbulence of the solar wind, is what truly determines how long it takes for these particles to reach us. Now, by mapping these ever-changing road conditions in space, we can better predict exactly when solar particles will hit Earth and how intense their impact might be. It's a major breakthrough for space weather forecasting, helping us protect satellites, astronauts, and even power grids on Earth. This isn't just science, it's vital for our technology-dependent world. Knowing whether electrons come from a flare or a CME lets us predict the risk and respond. Satellite operators, power grids, airlines, and astronauts all depend on accurate warnings. New missions like ESA's SMILE and Vigil will give us even more advance notice. We're entering a golden age of solar physics, finally understanding the chain from sun to Earth. By decoding these furious messengers, we're learning to protect our future. The sun gives us life, and now we're learning to live with its temper.